Okay, thank you. Great. These are basically electric circuits built from capacitors, inductance, and also Josephson junctions, which provides essential nonlinearity for building artificial atoms. These circuits are typically fabricated from aluminum, niobium, or tantalum and operate at microkelvin, millikelvin temperatures at gigahertz frequencies. From the original demonstration of superconducting qubits at late 90s, I guess it was 1991, 99. So for the last 25 years, this field emerged into a leading platform for realization of quantum computers, and it has a lot of advancements, such as demonstration of strong to ultra-strong couplings, demonstration of plethora of other types of interaction other than dipole, demonstration of so-called giant atoms regime of interaction, of light matter interaction, demonstration of quantum algorithms and quantum error correction, and so on and so forth. So this field is now thriving, it is evolving, but of course there are open questions, challenges, and one of these challenges is the lack of established, well-developed protocol approach for detecting microwave quanta. So in quantum optics, photodetection and photodetectors is a standard tool. Actually, it has a plethora of various applications, such as quantum state preparation, linear implementation of linear optic quantum computing, boson sampling, quantum key distribution, and many others. So one of the motivations of search for efficient detectors of microwave radiation operating at the level of individual quanta is to bring this toolkit from quantum optics to already developed field of certain quantum electrodynamics. And also there are other demands such as implementation of dispersive qubit readout, detection of electron spins, and also some applications from astrophysics, such as search of dark matter axions. And this first point, dispersive qubit readout, is a very important point. It is essential for successful realization of scalable, of large scale, practically usable quantum computers. So now I will outline one of the approaches to detection of microwave quanta in circuit quantum electrodynamics. Actually, it is one of the approaches. There are many proposals, theoretical and experimental demonstrations, and this one of such ways to detect individual microwave photons in superconducting circuits. These systems are called Josephson photomultipliers, and essentially these are qubits operating as narrowband absorbing detectors. And there are two generations of Josephson photomultipliers. The first generation is basically current biased phase qubit. It was demonstrated quite time ago. It is a Josephson junction biased by an external current. So we tilt, using this external current, we tilt its cosine-shaped potential to the point when we have only one potential well which can host metastable levels. If the transition frequency between these levels are close to the frequency of the incoming photon, then this photon induces a transition from the ground state to the excited state. Then, if this level is close enough to the top of the barrier, it can tunnel. So then excitation rolls down this potential and generates a voltage which can be detected. So this event signifies a click of a detector, signifies an arrival of a photon. However, this type of detectors has a significant drawback, since during this process, when the excitations jump out of the potential well and rolls down this washboard potential, it generates a lot of quasi-particles. Basically, our system heats up. So we need some time to let our system, our chip, cool down, to settle down, to perform the measurement again. So this limits its practical use. And the second type of, sorry, what's wrong? Example. Yeah, thank you. So other type of JPMs, which is more promising, especially for our applications, is based on the flux-based phase qubit. So instead of this washboard potential, we have potential which is basically a parabolic potential modulated by a cosine potential of a Josephson junction. So using the external flux, we tune the configuration of the potential to this two-well highly asymmetric configuration, when this shallow well contains only several levels, and the transition frequency between the bottom two levels is close to the frequency of the photons we try to detect. And so, as in the previous example, the incoming photon induces the transition to the upper level, and if the upper level is sufficiently close to the top of the barrier, the excitation can tunnel and then falls down to the global potential minimum. So instead of this continuous process of rolling down the potential, we have just one tunneling event, and we don't have these superfluous effects of heating up of the system. So with such a detector, we can repeat our measurements quite frequently, because we just need to read out the state, this change of the internal state of the detector, to figure out whether there was a clip or not. So this brings us to the idea whether we can use just one detector, which doesn't have photon-number resolution, because it can absorb only one photon at a time, so it cannot resolve between quantum states with different photon numbers. So can we use such a detector for counting photons? And in this regard, we consider this quite simple system. Resonator mode is capacitively coupled to the single Josephson photomultiplier of this second type. And we consider. So actually, our work is an attempt to answer the question: can we achieve some photon number resolution in this quite simplistic simple with minimum hardware resources? So this resonator can be implemented in various ways. It can be a lumped element in LC oscillator. Basically, it's a capacitor and an inductor, single mode LC oscillator. The second variant is a planar waveguide resonator. And the third variant is a microwave cavity. So it is a 3D cavity embedded in a piece of aluminum in this case. This is a photo detection procedure we consider. So first we start with preparing a quantum state in the resonator mode. At this stage, our detector is decoupled, so these manipulations with the state of the resonator does not influence the state of the detector at this point. So it is virtually inert to what we are doing with the resonator state. Then we adjust our potential to the this asymmetric configuration, to this working configuration when the detector is ready to absorb photons. Then we let the detector some time to interact with the motor of the resonator to absorb a photon. Then we perform a JPM readout. So we must detect whether this this absorption and tunneling occurred in the detector, and then we reset our detector, and then we again set it in this working configuration ready to capture photons, and we repeat this cycle several times, and at the end of the cycle, full cycles, we deduce how many photons we have detected. So we obtain some information about the state of the resonator node. So to describe this system, we derived an effective Hamiltonian after some simplifications and approximations, and we finally arrived at our Hamiltonian, which is actually a Jens-Cummins type Hamiltonian, nothing surprising here. So it is an oscillator interacting with the two-level system via the polar type interaction. Then to describe the dynamics of the system, we use master equation of the Lindblad type with this Lindbladian of a bit complicated form. So basically, we split our measurement sequence in two. So the first part is actually the part when we have active interaction between the motor of the resonator and the JPM. So it is photon capture time. And we describe it using this Lindbladian below. So here we account for the tunneling process, for the JPM relaxation, for the dephasing processes in the JPM, and also for the resonator losses. And the next part of our sequence is actually all these stages when we read out the JPM, when we reset JPM. So at these stages, our detector does not interact, of course, with some level of approximation, does not interact with the motor of the resonator. So on this stage, we have, and we actually are not interested in the processes of readout and reset. So we leave it behind our consideration. So on this stage, what we have some free evolution of the resonator mode and the relaxation. So we have some losses in the resonator, and it is described by the bottom limb. So next, actually, with this description, we have everything to determine what is going on in our system. We numerically solve this master equation, and we can calculate the probability of the JPM to deliver a click for the particular input state. In this case, it is an n-photon state. Probability of no click, it is actually 1 minus probability of getting click. So we have conserved probabilities, nothing, no surprises here. And we also account for the finite JPM readout efficiency. So we perform this readout stage, and actually we can have some errors, some non-idealities on the stage, even if our detector has correctly captured the photon, and we have all these processes of excitation and tunneling. As a result of the readout, we can still have some chance of erroneous outcome. So we describe this with some parameter beta, which we introduce by hand. Another important piece of information we can get from our master equation is the post-measurement state of the resonator field. So after each measurement, our field inside the resonator, it changes, and it change depends on the measurement outcome. So it is a conditional change depending on the outcome we get from our readout. With this information, so what we have here, we have probability of clicks, and we have information about the state of the resonator after each measurement. So with this information, we can compute the probability of obtaining a particular set of measurement outcomes. So what does it mean? So it means we have some set of outcomes, for example, several clicks, then no click, then also click, some set of outcomes denoted as IM. And it is actually quite important piece of information, which allows us to construct another important characteristic of our photocounter called positive operator value measure. So to determine photocounting statistics, we need we have Born's rule, which shows us that to determine the photocounting statistics, we for some initial state of the resonator field, we need to know some characteristic called positive operator measured value, which we can construct using these probabilities. So actually, what we need to know, we need to know the probability of to have k clicks given we have n input photons. But another question arises: how can we? What is the strategy for our counting? How do we count our photons? We consider two different strategies. First, the first strategy involves performing M measurement iterations regardless of their outcomes. So we set some number M and we iterate our measurement and determine the measurement outcomes. So for this strategy, the probability of k outcomes for n photon input state is basically the sum of probabilities of measurement outcomes with k clicks. So every permutation, every combination of measurement outcomes, which in total has k clicks. And we call this strategy binomial because in case it has some analogy with the binomial process. So in case we have equal probabilities of obtaining a click at each measurement stage, we would arrive at the binomial distribution. The next strategy is to repeat until we encounter no click event. So when we encounter no click event, we stop the measurement. So this is one condition. Or the other condition, we reach some maximum number of iterations. So in this case, we're interested only in the measurement outcomes which either have k consecutive click events terminated by no click event, or just m consecutive click events. So actually it is a core result of our work. Also, we need to somehow characterize the ability of our counter to resolve between between states with various photon numbers. So we should somehow tell how well can we resolve an M photon state from other states. So for this purpose, we introduce a measure and we investigate how the parameters of the system influences this measure. And we determine that for a fixed value of coupling strength between the resonator mode and the Josephson photomultiplier, and some fixed parameters of the resonator and the JPM, I mean loss rates, diffusion rates, we obtain some optimal capture times and optimal tunneling rates when we get the maximal resolution. So one way ask a question, why do we even have this limited capture time? So simple logic dictates us that maybe if we measure longer, then we would obtain better results. However, no. This limitation comes from the fact that we have false counts. So I'm just recall this scheme. So we, in addition to tunneling from the upper level, we also have some tunneling rate from the bottom level. So even if you don't have photons, input photons, we still have a chance to get a click event. So this is these false counts limit our measurement time. So we have some optimum time when we have maximal chance to get the correct result. So with here we see how how other parameters of the system influence this maximal resolution we get here. So we can see that increase of the coupling between the resonator and the JPM improves the situation. We see that larger relaxation in the JPM and the resonator gets the situation worse. So it's quite expected. So with these optimal parameters, we construct positive operator value measures for two strategies. And with this information, we can we can obtain photocounting statistics for some typical quantum states of the resonator field. Here we have, on the upper panel, we have a Fock state, and we have some comparison between the results of the ideal detector and different strategies in our setup. In the middle panel, we have a coherent state, and in the bottom panel, we have squeezed vacuum state. So to have some measure how close these distributions are, we use Hatacheria distance, and we have these numbers on each panel. So we can conclude that we have quite nice coincidence between actual photon-number distribution and the results we can get with just one detector. So what we have here, we considered an approach to count photons in the resonator by repeated measurements by a single Josephson photomultiplier. We derived PRMs for two counting strategies. We introduced the measure of photon-number resolution and studied its dependence on the setup parameters. And to conclude, we can see that with the state of the art and near-term circuit QD devices, we can actually achieve quite high degree of photon-number resolution. More details you can find in our published work, which was published last year. And there is some work in progress. So actually, it is a continuation of this idea with counting photons. So the idea here is quite simple. Can we somehow speed up this process of counting, and instead of counting photons one by one, can we count photons in pairs? So with this detector that can count photons in pairs, we can first of all speed up the process of counting, and we can arrange some composite photon-number resolution, photon-number resolving detector, which can be used in various applications in circuit QD, such as qubit readout and other applications. So also I would like to thank our quantum optics group here at BIPT, led by Dr. Andriy Semenov. Also thanks to our colleagues from Institute of Physics, National Academy of Science, and to our former BITP colleague and who is now in Yale Quantum Institute. So thank you for your time, for your attention. I hope something was useful for you, you have learned something new. Thank you. I'm ready for your questions.
Thank you, and thank you for a very nice talk. We'll see, what do we have? We don't have any questions in the chat, I think. We have a remark from Göran Johansson about a paper that he sent out. Maybe you can comment on that first, and then we can move on to questions.
Yeah, I raised my hand because I have a question.
Okay, then of course, then you go ahead and raise your hand, and then you make your question. Yes, please.
So thank you very much for a very nice talk. If I understand correctly, you count photons by removing them one by one.
Yes.
And so if you have many photons, then to get one photon into your counter, you need, I mean, basically, the more photons you have, the quicker is the stronger is the coupling, right? So if you know you have 5 photons, you should use a certain interaction strength for the first photon, and then you have 4, and then you would need a shorter time and so on. Did you consider such schemes?
No, in our scheme we have fixed interaction strength, which is optimized for just one photon. So if you have many photons, such an interaction strength may be a bit excessive, but we don't need to. There is no need to tune this interaction each step. So we have just fixed couplings, and we do not need something more, some other tunings, some other fields to tune.
But the interaction between the two-level system in your detector and the resonator, it's a Jaynes-Cummings interaction, or?
Yes. So it is simple capacitive coupling between these two subsystems, fixed capacitive coupling. So no squeeze, no in situ tunability. So just fixed couplings. The simplest setup, the simplest arrangement.
Yeah. So the more photons you have in the resonator, the quicker the first photon, then the quicker you excite your two-level system, right?
Yes.
So if you know how many photons you have, you could use a shorter interaction time for the first, and then scale them like
we assume that we have no prior information about the quantum state of the resonator, so we prepare ourselves for the worst case scenario when there is only one photon in the resonator.
Okay, thank you. Yeah, and the comment in the chat was simply that colleagues here at Chalmers University very recently published a paper where they call it digital homodyne and heterodyne detection, but they investigate a scheme where they remove one photon they interact with the cavity one photon at a time or so, and to look at Wigner functions and so on. So you might find that interesting.
Okay, thank you very much for this link. Thank you.
Do we have questions from the room on the in the Kyiv side?
Yes, we have.
Yeah, please. Why don't you speak up and you arrange the questions?
Yeah.
Okay. Could you show slide number 5, please? 5. Yes, previous. No, now it's next. Previous one. Previous. 5. Once again. Yes, here. Could you explain in more detail how you get the double well potential? Because in the first case, it's obvious that Josephson energy is cosine is periodic with phase, and because I don't see the scheme, Іван, приберіть, будь ласка, цю іконку, мінімізуйте її, sorry. Yes. Yes, but could you give more details how it becomes only double well?
Now, please speak up. We don't hear the answer here on the Zoom. I think you need to share the mic or something.
А зараз?
So what we have? We have this inductor on the right, which gives us parabolic potential. And we have contribution from the Josephson junction, which gives us a sine shape potential. So this modulation of the parabolic potential with the sine potential gives us for particular set of parameters, give us this dual potential.
So what you have in the scheme is just an inductance there, and that makes.
We have inductive both capacitive and inductive shunted Josephson junction, and we also have an external flux with this RF squid.
So it's a squid. Okay, thank you.
So it is basically a capacitive shunted RF squid.
Okay. Do we have further questions? I don't see any in the chat. Any more on the in the side of in the Kyiv room? Then I propose to thank the speaker again.
Thank you.
And move on to the last speaker of today. It's Göran Johansson from Chalmers University of Technology in Göteborg, Sweden. And I see Göran is moving, he's there. So he'll tell us about scattering from one and more atoms in waveguide QED. Please, Göran, the floor is yours.
I'll try to share my presentation here.
Yeah, it works fine.
Do you see my cursor here?
I see, at least, yes, absolutely.
Okay, good. So yeah, thank you very much for the invitation and the possibility to speak here. So I will talk about scattering from one and more atoms in waveguide QED. Yeah, I'll start to ask the question which I was asked now, I think maybe, yeah, towards 20 years ago. So yeah, my background is more superconducting circuits and circuit QED, as the last speaker mentioned. Then people from quantum optics asked me the following question, which was, if you have a two-level system and it interacts with the 1D waveguide, so you have an incoming photon which is on resonance with this two-level system, the question is, what is the maximum reflection you can get from a single photon? And then my spontaneous reaction was that, well, you know, it's absorbed because it's on resonance. And then it has a 50-50 probability of escaping to the left or to the right. But then I was told that no, this is not correct. Actually, if the photon is long enough, so to say, so that it's in frequency, it's fully on resonance with a two-level system, the scattering is a fully coherent event. So it's like a wave mechanics, and so basically you get the full 100% reflection. So you can just illustrate it with an incoming. If you think about in 2D or in open space, you can think about just a plane wave incoming light. Then it interacts with a dipole that then starts to emit light radially symmetric when it's excited. And then you just take the sum of those and you see that in the forward direction, there is perfect extinction, which implies that in this direction, everything just is reflected. And this is something which people have tried to realize with real atoms and with molecules. So, for example, in the group of Sandogar, And the problem here is that it's kind of difficult to get this to get when you use real atoms or molecules. They are small, so it's a little bit difficult to make them sit still, so to say, and also to focus your laser light so that you have a real 1D interaction. So in 2008 they managed to create a 12% extinction in the forward direction, which was they need to work quite hard for that. At that time we were working on these circuit QED, so these superconducting circuits where you use Josephson junctions to make artificial atoms, which was very nicely explained in the last talk. And then so the 1D waveguide is simply so-called microwave transmission line, which you make on chip. So, and it's basically just a squashed coaxial cable. So you can see here in the schematics here, you have a metal center conductor, and then you have the ground plane, which surrounds the coaxial cable, which are then just these planes outside here, and then the microwaves can propagate along this transmission line on chip. And then you simply insert one of these artificial atoms here in the gap between the center conductor and the ground plane. So then you have a capacitive coupling. And this is compared to real atoms, this is a really large object. So in this case, it was like a few hundred micrometers, and it's definitely sits still. And then you can send in microwaves here. In this case, the resonance frequency of this for these two levels of this artificial atom was 7 gigahertz. So you send in microwaves, and then you can measure the reflection and the transmission. And then you see here that so on this axis here, you have the power, the incoming power. And here on this axis, you have the transmission. So if you drive it very weakly, you see that you have almost no transmission. So if you check, you get 99.6% reflection. So, and then if you increase the power, this two-level system can then it reflects just one photon at a time. So if you send more than one photon per interaction time, it can no longer reflect, and then it will actually start to transmit. And if you send thousands of photons in an interaction time, they all just pass. So then you go towards unit transmission here. So this was an experiment done here at Chalmers University and published in 2011. Unfortunately, we were not the first to. So the NEC group in Japan, they were a little bit ahead of us. They were using a flux qubit instead of a transmon that we were using, and we managed to get a little bit better coupling here, so 99.6% instead of 94. But they were first. So then we looked at then we saw that indeed a single two-level system can reflect single photons fully. Now, then you can start to look at other properties of the scattered light. So, for example, you can look for the second-order coherence, and this is a quantity that you can measure by, for example, two photon counters, where you would have, if you have a single photon source here and you send it towards a beam splitter, then it can send only one photon at a time. So if you you can then get the click in either this photon counter or that photon counter, but never at the same time. But if you then, so you have to wait a little bit until you get the next click. And if you then calculate this G2 of tau, the second order coherence as a function of delay time. So that's basically the probability if you detect a photon at time t, what's the probability to detect another photon at time t plus tau, divided by the probability to detect photons at all in these two times. And then you see that this gives you information about the statistics of the light, which is interesting. So if you look at thermal light, just chaotic light from a light bulb, for example, then you see that there is actually an increased probability of detecting two photons at the same time. So indeed, the G2 of tau is 2 at 0 time delay, and then it goes down to 1 at long time delays. If you have a coherent state, or just what you get from a laser or from a microwave source, that corresponds to fully independent photons. So it's a Poissonian statistics. So if you detect a photon now, it has no so the probability to detect a photon at any time does not depend on when you detected the last photon. So in this case, the G2 of tau is simply 1 at all times. While if you have a single photon source, then your two-level system needs a little bit of time to reload before it can emit another photon. So then you have a 0 probability of detecting two photons at the same time, and then it goes up to unity here. So and this is then and this you for to have this type of G2, you indeed need a quantum source. The way this was measured was using so you have your qubit down here, and this just illustrates that you then use two linear amplifiers, so Hempt amplifiers, because we didn't have these single photon detectors, which indeed still are efficient single photon detectors are still missing in this toolbox. So here instead you do field amplification, so linear amplification. So and then to get these second order correlators in the power in photon-photon correlators, you actually need fourth order correlators in the voltage, in the field amplitude. And then you have with each measurement you have noise, so that you need to average for a long time. But then we checked that the measurement setup worked properly, so you could see that with a thermal state, you indeed get the G2 at 0 time difference of 2, and also you can see that the depending on the bandwidth of your measurement, you get different different widths here in tau, which is according to theory. And then you see that if you just have your microwave drive, which is Poissonian, you have G2 of tau, which is constant at 1. So that works. And then we looked at the reflected light or reflected microwaves here in the regime. So not at the really low power here, because then there was too much noise. So you need to go up a little bit in power. So it's around here. And indeed, so if it was ideally it should go down to 0 here for time 0 time difference, but we know we figured out the reasons why it didn't go down to 0 exactly. So it's both some kind of trigger jitter with the timing issue of the electronics, and also the finite bandwidth of the detection. So the theory here matched the reflection, the experiment well, and so we demonstrated that there is this anti-bunching in the reflected light. There is also another effect, which is in the forward direction. You see super bunching. So for zero time difference, there is actually a higher probability to detect 2 photons than for thermal light. So G2, which is of 0, which is larger than 2. And that was also then measured in a similar way. And you can see here that, so you see that G2 actually increases when you go to lower power, so it goes up. And according to theory, it should go up a lot, and that's simply because you can think about it this way, that you have an incoming coherent state, and the atom basically reflects a coherent state, the 0 and 1 photon component of a coherent state. But if there are 2 photons or more coming at the same time, that's then transmitted. So indeed, the transmission predominantly consists in the weak drive regime of photon pairs. And that gives you a really large G2 of tau in the weak drive regime. So this was now, early 2000, so more than 10 years ago. Now we actually came back to this question with a little bit of a detour, and we looked at what happens if you have more atoms in the transmission line. And during this time, this field has grown into, there are lots of experiments and lots of interesting things happening in this waveguide quantum electrodynamics. So it's an open 1D transmission line with one or more atoms in it. And you can realize it either with superconducting qubits or with cold atoms or with quantum dots. So there are different ways of realizing this. You see here in this overview that 2 things that you can categorize these different realizations is the number of emitters you can add, and there superconducting qubits, around 10 is probably where you want to go. I mean, you could probably add more, but yeah, 10 is probably a reasonable number. And then you see on this axis there is a different quantity, which is the coupling efficiency. So that is to what extent your atom couples to the transmission line and not to other relaxation channels, so you can emit photons sort of vertically or in a different mode. And with superconducting qubits, as you saw, you can make this 99.6 at that time, and you can get it up to more than 99.9% coupling to the transmission line today. Then so I just want to say that indeed, if you have more than one photon, and if you have more than one atom, in principle, this is a rather hard problem, because it's a many-body physics. You have the photon-photon interactions induced by the atoms. So this is in general a hard problem to look at, but we stumbled upon a solution here which we thought was interesting, where you can get analytical solutions also when you have a number of atoms in the transmission line. So so we simply put n atoms in the transmission line at either half or full wavelength in between. And if you do that, you get rid of the transmission line induced coupling between the atoms. So and you can describe the system basically that the ensemble of atoms interacts with the transmission line only through these collective operators, collective lowering and raising operators, and then you also drive it only through these collective operators. And the dissipation then also goes through this collective operator. So in this case, you can actually find, so if you want to see how this works for, from the circuit QED and distributed atoms to this model, you can just, there is a nice paper by the Alexander Blais group from 2013 doing this mapping. Then you end up with this master equation for the state of the two-level systems. And here we also neglected the individual dephasing or relaxation of the qubits to different channels. So we assume that that's negligible, which is for superconducting qubits, at least a decent approximation. And in that case, this ensemble of two-level systems remain in this in the Dicke sector. So you have basically in the fully symmetric states. So you can limit yourself to the n+1 states of these n emitters instead of the full 2 to the n Hilbert space. And then it was the steady state was found by Puri and Lavande in 1979. So you can write it like this, just in terms of these lowering and raising operators, and then there's a normalization factor here, and this basically corresponds to a type of coherent state. What we then noted was that if we look at now scattering from this, so you have the incoming drive from the left, then you have the outgoing field to the right and to the left. You have these input-output relations, and then you can actually rewrite the density matrix in terms of the inverse of the output operators to the right. So that's an interesting thing. And I also want to mention that here we neglect the time delay effects so we only take into account the phase gained by the field going between two atoms. So they cannot be too far away, so to say. Then we find that the transmitted field, just from this analytic solution, so the transmitted power is proportional to the drive amplitude to the power of 2 to the n+1. So so that basically implies that the transmission is an n+1 photon process. So yeah, you can plot it like this in the yes, so basically the transmission is proportional to the flux of incoming n+1 photon bunches in the drive, which is then Poisson distribution. So this you can find easily. So then we want to figure out sort of more about what's the dynamics of this. So we looked at the conditional state of the system after you have detected the first click in the output in the transmitted field. And so this is now numerical simulations for the 5 atoms at the moderate drive strength. And then you see that when you have the first click, you actually have a probability which is larger than 1/2 that all the 5 atoms are excited. And this is, you see that this is for rather weak drive. If you look at the steady state for this weak drive, you see that it's really mostly vacuum. So the excitation of the atoms is really weak, and of course then the transmitted field is very, very weak. But if you detected a transmitted photon, the probability that your atoms are excited is really large. So we find this rather interesting that you have this transmission, which is indeed in terms of these n+1 photon bunches. So you can then look at the histograms of the reflected and transmitted field, and you can actually also analytically find this is the probability given conditioned on the first click. So if you don't have a transmitted photon for a long time, this is the probability when you get the first photon that you have n atoms excited. And then you see that for n equal to small n is equal to big N, this is 0. So then this is more or less 1/2, just a little bit more. And the probability to have all but 1 excited is a little bit more than 1/4, and so on. Yes. So the conclusions here is that with n emitters, they reflect coherently the incoming drive up to n photons. If we have n+1 photons arriving in a time which depends, which corresponds to this collective interaction time, which then the more atoms, the quicker is the interaction, the faster is the interaction. So you need to have more photons on a shorter time with increasing n. So if you have this n+1 photon bunches arriving in this time scale here, you have a transmission. So basically what happens is that you have all the atoms get excited, and then they relax equally to the left and right, which give you then on average n+1/2 photons that are transmitted. And then you can also find, as I mentioned, the probability distribution of the excitation of the atoms after the first photon. So this is work mainly done by Zeidan, who is in the Zoom, and also now PhD Therese Karmstrand and Mariam Kamanadi, who is a postdoc here, and we are writing this up. I just want to mention that the reason that we sort of got into this system again was a little bit of a detour through quantum plasmonics work, which was done by Therese Karmstrand, and that was basically a Tavis-Cummings model. So it was an ensemble of 2-level systems coupled to a cavity. So the difference is mainly the cavity. And then we saw in that work that in a certain regime there, when you drive on resonance, you have that basically the 2-level systems act like a coherent, they start to oscillate coherently, and they cancel the drive. So basically you get a low, so this is now the occupation of the cavity as a function of the drive strength, and then this would be if you were driving the cavity without oscillators, without two-level systems. But then the on resonance, this is suppressed a lot. And then you see that depending on the number of two-level systems, you saturate the two-level systems in different ways. And you see that it's indeed just to say that the absorption there, or the how you go from how you saturate the system is then again an n+1 photon process. So there we saw that basically the cavity can, if you have two atoms, it can reflect single 1 and 2 photon states. But if you have the 3 photons coming in simultaneously, they will be absorbed by the cavity, and then we could explain the dynamics by just looking at these type of n+1 photon absorptions in the cavity. And yes, and that was previously published work with Therese. Yes, thank you very much for your attention.
I'm sorry, we lost the sound.
Oh.
For me, actually, it's my mistake. Yeah.
Yeah.
So we have a question first from Mats Larsson, and then before there was also a question from Danilo Yakumenko, but maybe that was only to tell that the sound was gone. Okay, so for the moment we have Mats Larsson, please.
Okay, Göran, thank you very much for a very interesting talk. It's obvious that this is a very vibrant field, I mean, waveguide QED, and with several different platforms. So my question is, do you see some real applications of this in the near future, and what would that be?
So I'm not sure if so like real applications for technology, or
yes, quantum technologies, exactly.
Yeah, I'm a little I don't have that on top of my mind. I think what I find interesting is this you can work with the giant atoms, for example, where you have an atom that's coupled to the waveguide in multiple places. And with this you can make the coupling chiral, and you can but so that you can use for designing quantum simulations. I think so. MIT demonstrated that with I think 2 giant atoms in Bill Oliver's group, but I haven't. No, on top of my head, I don't see any immediate quantum technology applications for this. I find it very stimulating to think about, though. But yeah.
Okay, thanks.
Okay, so next speaker, next question in the chat is from Andriy Sotnikov, please.
Yes, thank you for the nice pedagogical talk. I find results very interesting. In particular, we are in Kharkiv. We are thinking of developing experimental quantum optics course with the equipment, and I was wondering how is it feasible to implement your maybe previous set of your experiments into master course? Is it demanding for costly equipment, or you can do more or less the same with cheaper analogs? Could you comment a bit?
So that it's a good question. I mean, for the superconducting circuit experiments, you would need a dilution refrigerator. Yeah, which is very costly. So I'm thinking whether if there is one of the other systems that is. I mean, typically for cold atoms, you also need ultra high vacuum and so on. That's difficult. I have quantum dots, but typically they are also cooled down to get good coherence. But yeah, I guess that the quantum dots would be the maybe, but I'm no expert there. So, but in photonics might be where you can where you could realize this more straightforwardly. Yeah.
Yeah, thank you.
Okay. Do we have other questions? Questions from the audience on the Bogolyubov Institute side?
Yes, Eric, may I ask a question?
Of course, of course.
Larissa Bridget, thank you so much, Goran, for your very interesting talk. And my question is, I am really impressed by your results and your approach, really very educative. And I found some analogy naive. Maybe this scenario is realized in the living matter. We have electromagnetic field inside. It is self-focused in some kind of waveguides. And maybe it works. What do you think? Well, I understand that's very difficult to measure, to check in vitro or in vivo, but still. Well, thank you.
Yeah, no, it's a very interesting question. I don't know enough about this to have a good insight, but I definitely think about it.
Yeah. So maybe I can follow up a question to Larissa. Did you have the Danilov soliton in mind, or kind of transmission in neural signals, or is it in the chlorophyll and the transmission of?
Well, in my opinion, this system of channels of waveguides has different sources of origin. So the width of soliton is one of them. A neural network is another one. And all this works supplementary. But we can check this on each particular mechanism, for instance, the width of solitons, which are more close for me. Because we have interaction electromagnetic field with matter. We have self-focusing due to nonlinear characteristics of the living matter. And it seems that it should work.
All right. Do we have more questions in the room in the Kyiv side?
Seems no. Thank you.
Then I believe we are done for today. I think there will be a continuation. At least there will be discussion about the continuation between me and Mats Larsson and Professor Bridzik, and we will, yes, we will find out what is the interest and circulate the next plans later, I think. Is that correct, Larissa?
Yes, Eric, thank you so much. And if can I have 1 minute more?
Of course.
Our director, Sergei Peripolitsa, had to leave at 1 p.m. because he has another meeting at the Presidium of the Academy of Sciences, which is quite distant, but